solution sets of equations are usually pretty boring. Equations typically have one or a few solutions, and we can just list all of the numbers that are solutions. And that's fine, but it's not a very interesting set. Occasionally something weird happens and an equation doesn't have any solution, or every number is a solution. But in general, equations give boring solution sets. Inequalities, on the other hand, typically have infinitely many solutions. So, some but not all of the real numbers are solutions to this inequality. Infinitely many of them are. So that's an interesting set, and we'd like to have a way to describe it. What do I mean when I say they have infinitely many solutions? I mean, I can just keep coming up with numbers that are solutions to a particular inequality. So, x is greater than 2. Any number that's greater than 2 is a solution to this inequality. So 7 is a solution, because 7 is greater than 2. 863 is a solution, because 863 is greater than 2. And even like 2.001 is a solution, because that's a little bit greater than 2. So I can just keep coming up with numbers that are greater than 2. Y is less than or equal to 0. Again, many solutions, right? Negative numbers are solutions. -6 is a solution, because -6 is less than or equal to 0. Now in this case, right, my numbers are allowed to equal 0, so 0 is a solution. 0 is less than or equal to 0. And numbers that are tiny little negative numbers, -0.005, those are also solutions to this inequality, because negative a tiny little decimal is still less than 0. For one of these between type inequalities, we need something for z here. So -4 is less than z is less than or equal to 7. We need something that -4 is less than. So we need something that's bigger than -4 and less than or equal to 7. I mean, 7 works, because -4 is less than 7, which is less than or equal to 7. But, like, -4 wouldn't work, because it's not true that -4 is less than 4. We could take something a little bit bigger than -4, so like maybe -3.9. Then -4 is a little bit less than -3.9, which is less than or equal to 7. And then we can pick anything in between there, so like 2. -4 is less than 2, which is less than or equal to 7. Right? There are lots of numbers between -4 and 7, and any of those is a solution to this inequality. One more. 1 is greater than x is greater than 0. So our value x has to be between 0 and 1. There aren't any integers in there, right? Because it goes 0 and then 1. So we're going to need fractions or decimals that are less than 1, right? So like a half. Definitely 1 is greater than a half, and a half is greater than 0. Or we could pick some decimal, right? We could say 0.27. Right? 1 is greater than 0.27, which is greater than 0. Or, we could be weird and pick like 0.4 repeating. That's a decimal that's between 0 and 1. Right? 1 is greater than 0.4 repeating, which is greater than 0. Right? So even if we have two consecutive integers, there are infinitely many decimals in between there. So how can we represent these solution sets? We can't just list all the numbers because there's infinitely many. When we're trying to represent an infinite solution set, one of our go-to tools is a graph, a picture of the solution set. We're talking about one variable, so the kinds of graphs we're talking about are going to be graphs on a number line. How do we do this? To graph an inequality on the number line, we take the numbers shown in the inequality, we mark them with a closed dot if that number is a solution, so if equals is allowed, an open dot if that number is not a solution, and then we shade the other numbers that are solutions. So here I have x is greater than 2. I'll put an open dot at 2, and then I'll shade all the numbers that are greater than 2. Sometimes when I'm drawing this by hand, instead of graphing on top of the number line, I'll put my graph a little bit above the number line just so that I can see it better. When we're in print, we'll typically use colors to indicate our number lines, or else we'll make sure that our print is very thick. But by hand, it can be useful to just draw above the number line. Y is less than or equal to 0. So I'll put in a filled dot at 0, and then I'll shade all the numbers that are less than that. Z is between -4 and 7. We'll have an open dot at -4, a filled in dot at 7, and we'll connect those. 1 is greater than x is greater than 0. We'll have an open dot at 0, an open dot at 1, and we'll connect those. How do we decide which direction to go? Well, if we have one of these between inequalities and it's written correctly, we know we can just connect the dots. If we're looking at greater than, the numbers greater than a given value are the numbers to the right of that value. If we're looking at less than, the numbers less than a given value are the ones to the left of that value. So just think about the relationship, and then think about what numbers are solutions, and shade those numbers. In this next example, we're going to be given some graphs, and we're going to be asked to write the inequalities. And of course, we've just got this number line here. We need an instruction to tell us what to name the variable. So we have an instruction here telling us to use x as our variable. Without that instruction, we can kind of pick whatever variable label we want. So let's look at these graphs. So here I have 2 endpoints, right? So my x is going to be between 2 numbers. The minimum number is -4. The maximum number is 3. I've got a closed dot at -4, so -4 is allowed to be a solution. I've got an open dot at 3, so 3 is not allowed to be a solution. And as long as I go from left to right, the inequality symbols I'm going to use are going to be less than. Now, if I wanted to, I could also go right to left, right? I could put the 3 first, then the x, then the -4. If I'm going right to left, the inequality symbols I'm going to use are going to be greater than. Right, so 3 is not allowed as a solution, -4 is. If I'm going right to left, I'll use greater than and greater than or equal to. In general, at least if we're working in English where we read left to right, it's just more natural to go left to right. So if I'm writing down one of these between inequalities from a number line, I'm going to go left to right and use less than symbols. And so here, I've got the region between 3 and 5 shaded. So x is going to be between 3 and 5. 3 is allowed to be a solution, so we'll say less than or equal to. 5 is also allowed to be a solution, so we'll say less than or equal to again. So these first two, where I have 2 ends, I'm going to use one of my between inequalities. These next two, I only have 1 end, so this is just going to describe a relationship between x and a number. So We're looking to the left of -2. So we're looking at numbers that are less than -2. And -2 itself is not allowed to be a solution. So this is just a less than, not a less than or equal to. Here, we're describing a relationship between x and -3. We're going to the right of -3, so we're going to use a greater than. -3 is allowed to be a solution, so we're going to have greater than or equal to. So now we've talked about taking an inequality and making its graph, going from the graph back to an inequality. It turns out these graphs of inequalities are a really useful way to think about some really common kinds of sets that we're going to meet throughout the course. In the next video, we're going to meet a special notation that we use to describe this kind of set.